Geology is a science that deals with the history and structure of the earth and its life forms, especially as recorded in the rock record. A basic understanding of its concepts and processes is essential in the petroleum industry, for it is used to predict where oil accumulations might occur. The purpose of this chapter is to outline the geologic requirements for exploitable fossil fuel and geothermal resource. Conventional fossil fuel categories covered in this chapter include coal and conventional oil and gas. In this chapter, we will discuss about geology of coal, geology of petroleum and gas. Coal is a brownish black to black combustible organic sedimentary rock formed by the decomposition of plant material, typically in a swampy or boggy environment. This organic material called peat is buried, compacted and hardened over millions of years. This process is called coalification. During coalification, peat undergoes several changes as a result of bacterial decay, compaction, heat and time. Peat deposits are quite varied and contain everything from pristine plant parts, roots, bark, spores, etc. to decayed plants. The coalification of peat passes progressively through four main phases of coal development: lignite, subbituminous coal, bituminous coal and anthracite. These end products are composed primarily of carbon, hydrogen, oxygen and some sulfur along with water, moisture and non-combustible ash. The rank of coal is based on the amount of carbon and volatiles, water and gas in the coal as well as the energy content of the coal. The amount of energy in coal is expressed in British thermal units (BTU) per pound. The higher a coal's rank, the greater its heating value. The coal can be mined by the surface method, complete removal of overburden, or deep underground method based on the amount of ground cover or overburden. Today, we can mine more tonnage of coals with less manpower because of the tremendous advancement of mining technology. In fact, present world use only 10% of employees than the coal mining employees in 1940-50. Coal formation coalification. The process of coal formation is known as coalification. Peat is an accumulation of partially decayed vegetation matter. Peat deposits could contain everything from pristine plant parts, roots, barks, spores, etc. to decayed plants, decay products and even to charcoal if the peat is caught fire. Peat deposits formed in a waterlogged environment. Wet condition also reduces chemical decay of the plant materials where plant debris is accumulated, for example, peat bogs and peat swamps. The accumulation of plant debris exceeds the rate of bacterial decay of the debris as the available oxygen in organic rich water is completely used by the decaying process. For the peat to become coal, it has to be protected from oxygen. Oxidizing environment can form coal and must be buried by sediment. Burial promotes the compaction of peat and helps water to squeeze out during the early stages. Formation of peat is considered the biochemical stage of coal formation. During this stage, plant residue partially decomposes, degradation of plant cellulose materials. Some authors call the stage of peat formation as the humification stage. Once the peat is buried under thick sediments, it is subject to high temperature and pressure over a long period of geologic time. The geochemical stage is the irreversible and continuous process that turns the peat into sedimentary rock. Conversion of lignin into humic substance and condensation of humic substance to form larger coal molecules. Diagenesis and metamorphism gradually turns the peat into lignite, subbituminous, bituminous and anthracite with increasing temperature. The geochemical process due to diagenesis and metamorphism that changes the peat into humic coal series is called the coalification stage. During the coalification stage, physical properties such as color, luster, hardness, specific gravity, porosity, vitrinite reflectance. Texture and structure of the coal forming minerals are substantially changed. Phase 1 aerobic decay. In the first few inches of peat, aerobic oxygen-loving bacterial decay reduces the volume by as much as 50%. The bacteria soon use up all the available oxygen and die due to impermeable nature of the peat and water being stagnant. Anaerobic bacteria, which can live in oxygen-poor environment, now continue the decay process, reducing the volume still further. Aerobic decay produces more acids, and when the acidity gets too high, it becomes toxic for the anaerobic bacteria and all decay processes stop with the death of the organism. After the completion of initial bacterial decay stages, the peat must be buried under thick sediment that acts an insulating layer, trapping the natural heat rising to the surface. The bituminization process begins when the temperature reaches 100 degrees, 212 degrees Fahrenheit. Chemical reactions drive off water, oxygen and hydrogen, which raise the percentage of carbon during this process. As the burial continues, addition of heat and time causes the complex hydrocarbon compounds to break down and alter in various ways. The gaseous alteration products such as methane are typically expelled from the deposit, making the formation richer in carbon content over time. It could take millions of years to convert peat to anthracite coal. Both temperature and pressure play important role during the stages of geochemical process. There is some disagreement about temperature or pressure being the most important factor. One other factor is time. It could take millions of years for the peat to turn into coal under right temperature and pressure. It is estimated that about 10 vertical feet of original peat material is needed to produce 1 vertical foot of bituminous coal due to squeezing and compaction of peat material. Some scientists believe that the coal formation is always in situ. The coal forming plants grew in swamp area. Erosion subsidence buried the plant debris and formed coal bed over time. Humic coals fall under this group. Humic coals form in the lakes, swamps, bogs and lagoons with dense forests. In situ coals are thereby autochthonous. The Great Swamp of Georgia in the US is an example of such coal formation. Some scientists believe in drift theory for coal formation. According to this theory, the plants grew in different areas. The plant debris is carried to the depositional basin by current. Trees along the river channels are drifted downstream. The plant remains could then accumulate with other sediments on the sea floor. In reality, the formation of coal involves both theory discussed above. The plant debris could accumulate in situ at a location but occasionally transported by water into depositional environment. Factors affecting coal formation. There are several factors that control the coal formation: nature and chemical composition of source plants, climate, paleogeography, depositional environment, tectonics, time. Coal availability in India. Coal deposits in India are of two distinct geological ages. The earliest coal deposits are of Permian age, formed about 270 million years ago. At that time, South Africa, South America, Antarctica, Australia, India and Madagascar formed a land mass called Gondwana land. Coal formed in Gondwana land is known as Gondwana coal. Other deposits of tertiary age, Eocene, 30 to 60 million years, have been formed comparatively recently. These are known as tertiary coal. India has the 5th largest coal reserves in the world. Of the total reserves, nearly 88% are non-cooking coal reserves, while tertiary coal's reserves account for a meager 0.5% and balance is coking coal. Indian coal is characterized by high ash content of up to 45% and low sulfur content. The commercial coal in the country is mainly consumed by the power, steel and cement sector. The Indian coal deposits are primarily concentrated in the Gondwana sediments, upper Paleozoic to Mesozoic systems, occurring in the eastern and central parts of peninsular India. The coal is of bituminous to subbituminous rank and is restricted to the sediments of Permian age. The tertiary coal-bearing sediments are found in northeastern India, spreading over the states of Assam, Arunachal Pradesh, Nagaland and Meghalaya, of which the Assam coal fields are the prominent ones. Indian lignite deposits occur in the tertiary sediments in the southern and western parts of the peninsula shield, particularly in Tamil Nadu, Pondicherry, Gujarat, Rajasthan and Jammu and Kashmir. A total of 298.214 billion tons of geological resources of coal have so far been estimated in India up to the maximum depth of 1200 meters. Out of the total resources, the Gondwana coal fields account for 2,97,421 MT, 99.5%, while the tertiary coal fields of Himalayan region contribute 1,493 MT, 0.5% of coal resources. As of April 2013, prime coking coal contributes about 79% to the coal reserves of the country, with medium and semi-coking coal contributing about 16 to 5% respectively. The inventory of geological resources of Indian coal is prepared by the Geological Survey of India. Coal exploration in India. The objective behind carrying out the exploration activity is to identify an economic coal mine. The process involves identification of mine, collection of data and use of information in the feasibility study for the coal mining project. The exploration for coal and lignite is a multi-stage pursuit involving a plethora of activities beginning from preliminary investigations to regional promotional exploration and culminating into the modeling of the resource for projects. Exploration for coal in the country is carried out in two broad stages, that is, regional exploration and detailed exploration. The regional exploration for coal is carried out by the government organization, whereas detailed exploration is largely undertaken by coal companies. Although drilling is the most important activity involved in coal exploration, it cannot be considered the beginning and the end in itself, as proper conceptualization and modeling of the resource is essential to present a sound base for efficient and optimal exploitation, with due consideration to conservation of the precious non-renewable energy source. Sink drilling activities. Continuous monitoring and interpretation of data being generated and modification of exploration program depending on the results, advising for coal analysis, etc. Post-drilling activities, conducting various types of analysis, interpretation of the complete data and modeling and assessment of the coal resource. Classification of coal in India. Depending upon its grade from highest to lowest following, the coal found in India can be classified as anthracite coal, bituminous coal, lignite, brown coal, peat, etc. Anthracite coal. This is the best quality of coal and contains over 85% carbon. It is very hard, compact, jet black coal having semi-metallic luster. It ignites slowly and burns with a nice short blue flame. In India, it is found only in Jammu and Kashmir, and that too in small quantity. Number 2. Bituminous coal. This is the most widely used coal and contains 50 to 85% carbon. It is dense, compact and brittle and is usually of black color. A good bituminous coal is composed of alternate dull and bright bands. Its calorific value is very high due to high proportion of carbon and low moisture content. Most of the bituminous coal is found in Jharkhand, Orissa, West Bengal, Chhattisgarh and Madhya Pradesh. Number 3. Lignite, brown coal. Also known as brown coal, lignite is a lower grade coal and contains about 35 to 50% carbon. It represents the intermediate stage in the alteration of woody matter into coal. Its color varies from dark to black brown. It is found in Palna of Rajasthan, Naveli of Tamil Nadu, Lakshmipur of Assam and Kairawa of Jammu and Kashmir. Number 4. Peat. This is the first stage of transformation of wood into coal and contains less than 35% carbon. It is seldom sufficiently compact to make a good fuel without compressing into bricks. Left to itself, it burns like wood, gives less heat, emits more smoke and leaves a lot of ash after burning. Coal reserves in India. Coal reserves in India as per Indian Standard Practice (ISP) guidelines. ISP does not distinguish between resources and reserves. Are classified under three categories: proved, indicated and inferred geological reserves. Proved geological reserves represent a resource base with the highest confidence. The delineated tonnage within an area falling within a radius of 200 meters around boreholes is categorized as proved geological reserves. Proved geological reserves can be produced only on the completion of detailed exploration. Indicated geological reserves comprise that material occurring within a radius of 1000 meters around boreholes taken up for regional and detailed exploration. While estimating indicated geological reserves, qualitative information obtained from the regional exploratory boreholes are projected in the indicated geological reserve category. Inferred geological reserve comprise that material occurring within the influence area beyond 1000 meters and up to 2000 meters from the point of observation. Oil and natural gas were formed from the remains of prehistoric plants and animals. That's why they are called fossil fuels. Hundreds of millions of years ago, prehistoric plants and animal remains settled into the sea along with sands, silt and rocks. As the rocks and silt settled, layer upon layer piled up in rivers, along coastlines and on the sea bottom, trapping the organic material. Without air, the organic layers could not rot away. Over time, increasing pressure and temperature changed the mud, sand and silt into rock known as source rock and slowly cooked the organic matter into petroleum. Petroleum is held inside the rock formation, similar to how a sponge holds water. Over millions of years, the oil and gas that formed in the source rock deep within the earth moved upward through tiny connected pore spaces in the rocks. Some seeped out at the earth's surface, but most of the petroleum hydrocarbons were trapped by non-porous rocks and other barriers. These underground traps of oil and gas are called reservoirs. Reservoirs are not underground lakes of oil. They are made up of porous and permeable rocks and can hold significant amount of oil and gas within their pore spaces. Some reservoirs are hundreds of feet below the surface, while others are thousands of feet underground. Petroleum exploration. The fundamental goal of petroleum exploration is to identify areas with the right geologic condition which are known to be capable of creating an accumulation of petroleum. Economically viable resources can only be discovered via drilling operations in such target areas. The oil and natural gas that power our homes, transportation and businesses are found in small spaces called pores between layers of rock deep within the earth. Many offshore wells, for example, are drilled in thousands of feet of water and penetrate tens of thousands of feet into the sediments below the sea floor. Natural gas is usually found near petroleum. Oil is then transported to refineries and distilled into fuel or base chemical products. Natural gas is pumped from below ground and travel in pipelines. Petroleum reservoirs. Petroleum reservoirs are generally classified according to their geologic structure and their production drive mechanism. Geological classification of petroleum reservoirs. Petroleum reservoirs exist in many different sizes and shapes of geologic structures. It is usually convenient to classify the reservoirs according to the conditions of their formation as follows: dome-shaped and anticline reservoirs. These reservoirs are formed by the folding of the rock layers. Faulted reservoirs. These reservoirs are formed by sharing and offsetting of the strata, faulting. Salt dome reservoirs. This type of reservoir structure, which takes the shape of a dome, was formed due to the upward movement of large impermeable salt dome that deformed and lifted the overlying layers of rock. Unconformities. This type of reservoir structure was formed as a result of an unconformity where the impermeable cap rock was laid down across the cut-off surfaces of the lower beds. Lenses type reservoirs. In this type of reservoir, the petroleum bearing porous formation is sealed by the surrounding non-porous formation. Combination reservoirs. In this case, combinations of folding, faulting, abrupt changes in porosity or other conditions that create the trap from this common type of reservoir. Petroleum production. Petroleum production is the overall term given to the process of extracting a hydrocarbon reserve from an economically viable subsurface discovery. Before mining takes place, operators will usually have done both prospecting and exploration in the area of accurately delineate the petroleum field. Estimate the production life of the field. Once discovery appraisal operations are complete, it is necessary to estimate how big the resource is, what is expected to be produced, that is crude oil, condensate or natural gas, and the specific chemical composition of such products. This and other technical information will allow the expected production life of the field to be estimated. Design production facilities. The engineering design process considers all this information along with the geographic location of the resource, that is water depth, and aims to design appropriate infrastructure to ensure the safe, effective and efficient extraction of the resource. The most important thing of all stakeholders is that the development and design are fit for purpose and will operate safely for the extent of the field's production life. This point of development in the exploration production cycle represents the greatest reliance on surface and subsurface infrastructure. Commercial production. Once all infrastructure requirements are built and appropriately commissioned, the development project then moves into a production phase which involves 24 hours a day production, processing and transport of the petroleum products to market. Dependent on resource volumes and daily production requirements, production operations can last for decades. Drilling, engineering and operations. Following the preparation stage of field development, that is, setting the production strategy, determining the locations of the wells in the field and designing the well completions, the drilling related activities begin. The drilling program consists of three main stages. Number 1, drilling the hole to the target depth. Number 2, setting the various casings. Number 3, cementing the casing. Petroleum refining. Petroleum refineries are large, capital intensive, continuous flow manufacturing facilities. They transform crude oils into finished refined products, most notably LPG, gasoline, jet fuel, diesel fuel, petrochemical feedstocks, home heating oil, fuel oil and asphalt, by separating crude oils into different fractions, each with a unique boiling range and carbon number distribution. And then second, processing these fractions into finished products through a sequence of physical and chemical transformations. Refinery processes primary crude oil cuts in a typical refinery include gases, light, heavy, naphtha, kerosene, light gas oil, heavy gas oil and residue. From these intermediate refinery product streams, several final product streams such as fuel gas, liquid petroleum gas, LPG, gasoline, jet fuel, kerosene, auto diesel, lubricants, bunker oil, asphalt and coke are obtained. The entire refinery technology involves careful manipulation of various feed properties using both chemical and physical changes. Crude distillation. The first essential task for the crude oil consisting of more than 10 compounds is to separate its major components based on boiling point differences. This principle is exploited in the crude distillation unit, which involves energy intensive operation. Since crude distillation involves the processing of the entire feed, it remains as the most significant operation in a refinery. Natural gas. Natural gas is principally methane, CH4, with some ethane, C2H6, and propane, C3H8, and impurities such as CO2, H2S, and N2. Natural gas is a versatile fossil fuel that we use for heating, cooking, electricity production, and transportation, and as an industrial feedstock. Formation of natural gas. Like oil, natural gas is a product of decomposed organic matter, typically from ancient marine microorganisms deposited over the past 550 million years. This organic material mixed with mud, silt, and sand on the sea floor, becoming gradually buried over time. Sealed off in an organic-free environment and exposed to increasing amounts of heat and pressure, the organic matter underwent a thermal breakdown process that converted it into hydrocarbons. The lightest of these hydrocarbons exist in the gaseous state under normal conditions and are known collectively as natural gas. In its pure form, natural gas is a colorless, odorless gas composed primarily of methane. Methane, the simplest and lightest hydrocarbon, is a highly flammable compound consisting of a carbon atom surrounded by 4 hydrocarbon atoms. Chemical formula CH4. After natural gas forms, it will tend to rise towards the surface through pore spaces in the rock because of its low density compared to the surrounding rock. Most of the natural gas deposits we find today occur where the gas happened to migrate into a highly porous and permeable rock underneath as impervious cap rock layer, thus becoming trapped before it could reach the surface and escape into the atmosphere. Production. Conventional natural gas deposits are commonly found in association with oil reservoirs, with the gas either mixed with the oil or buoyantly floating on top. Natural gas can be located with seismic methods similar to those used for petroleum exploration. Gas prospectors set off an explosion on the surface to generate seismic waves in the underlying rock. By measuring the travel times of these waves through the earth at acoustic receivers known as geophones, geophysicists can construct a picture of the subsurface structure and identify likely gas deposits. To extract the gas, vertical wells are drilled to penetrate the overlying impermeable cap rock and reach the reservoir. Natural buoyancy then brings the gas to the surface where it can be processed and sent to the homes and industry. Natural gas comes in 4 basic forms. Number 1, liquid natural gas, LNG. Natural gas which has been liquefied at minus 160 degrees centigrade. Natural gas is liquefied to facilitate transportation in large volumes in cryogenic tankers across sea. Second, regasified liquefied natural gas, RLNG. LNG regasified before transporting it to consumers through pipelines. Number 3, compressed natural gas, CNG. Natural gas compressed to a pressure of 200 to 250 kg per centimeter square, used as fuel for transportation. CNG decreases vehicular pollution on the virtue of being cleaner fuel than liquid fuels. Number 4, piped natural gas, PNG. Natural gas distributed through a pipeline network that has safety valves to maintain the pressure, assuring safe, uninterrupted supply to the domestic sector for cooking and heating, cooling applications. Resources and reserves. India has 1074 BCM of natural gas reserves. This includes 287 BCM of natural gas from onshore and 787 BCM offshore. In terms of gross production, the figures stand at 32,849 MCM. Of this, 8,763 MCM of natural gas is produced onshore and 24,086 MCM offshores. However, the net production of natural gas during 2008-09 was 31,770 MCM.